At the end of the last episode, we hit a wall. You can run a real AI model on your own laptop, but only if it fits in your memory, and the best open models are enormous. A 70 billion parameter model stored the normal way is around 140 gigabytes. No laptop on Earth has that much memory to spare. And yet, we just told you people run models like that on a good machine at home. So either we were lying, or there is a trick. There is a trick, and it is one of the most important and underappreciated ideas in all of practical AI. It is called quantization, and it is the reason local models exist at all. Today we open it up, and you will see how 4 bits can shrink a model fourfold without wrecking it. Quick note, before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. To understand quantization, you have to remember what a model actually is underneath. From episode 1, a model is its parameters, also called weights, and a weight is simply a number. A modern model is just billions of these numbers sitting in a giant file that together encode everything it learned. Now here is the detail that unlocks the whole episode. Each of those numbers is normally stored at high precision as what is called a 16-bit floating point number. A floating point number is just a number with a decimal point, like 0.07391, and 16 bits is how much computer space it takes to write each one down accurately, which works out to 2 bytes per weight. Multiply 2 bytes by 70 billion weights and you get your 140 gigabytes. So the size of a model is not really about its intelligence. It is about how many numbers it has, times how precisely each one is written down. And that second part is something we can change. So here is the whole idea in one sentence. Quantization is storing each of the model's numbers at lower precision, using fewer bits to write each one down, so the whole model takes up far less space, while staying close enough to the original that it barely loses any intelligence. The most common move is to go from 16 bits per weight down to 4 bits per weight. 4 bits instead of 16 is 1/4 the storage, so your 140 gigabyte model becomes roughly 35 to 40 gigabytes and your 8 gigabyte model becomes about 2. Suddenly it fits. That is the entire magic. You did not throw away any of the billions of weights. You kept every single one. You just wrote each of them down a little less precisely. Now the obvious worry. Surely making every number less precise makes the model dumber? And the genuinely surprising answer is, almost not at all, as long as you do not push too far. There are 2 good ways to feel why. First, think of rounding. The number 3.14159 and the number 3.1 carry almost the same meaning for most purposes. You lost a little precision, but you kept the essence. Quantization is doing that to billions of weights at once, nudging each to a nearby, coarser value. Second, and even better, think of a JPEG photo. A raw image is huge, but a JPEG throws away detail your eye barely notices and comes out a fraction of the size while still looking like the same picture. Quantization is the JPEG of AI models. It compresses by being a little less exact, and the result is so close to the original that, for most tasks, you would never know. The deeper reason this works is that these models are overbuilt. They have so many weights, with so much redundancy, that they are remarkably tough against a little numerical noise. No single weight is precious, so rounding all of them gently leaves the overall behavior almost intact. But there is a floor, and knowing where it is matters. Going from 16 bits to 8 bits is essentially free. You will not notice any difference at all. Going to 4 bits is the famous sweet spot, where you get the big size savings for only a tiny, often invisible, drop in quality on the order of 1% or 2% on most tasks. But keep squeezing, down to 3 bits, then 2 bits, and the model falls off a cliff. At 2 bits, it starts making real mistakes, losing the thread on anything that needs careful reasoning, getting facts wrong, becoming visibly less sharp. So the rule of thumb the whole community has landed on is simple. 4-bit is the line where you get almost all the savings for almost none of the pain. Below it, you are trading away real intelligence for a little more space, and it is usually not worth it. This is why when you download a model to run locally, the 4-bit version is very often the one you want. Now, when you actually go to download one of these, you will run into a soup of cryptic labels, and a couple of minutes of decoding them will save you real confusion. The most common format for running models on a laptop, especially through Ollama, is called GGUF, and inside it you will see options like Q4, KM. Let me decode that because it is not random. The Q stands for quantized. The 4 means 4 bits. And here's the clever part, the K and the M. A smart format does not crush every weight equally. It recognizes that some layers of the model are more sensitive than others, so it keeps the most important weights at a higher precision, say 6 bits, while squeezing the rest down to 4. The K marks that kind of mixed sensitivity-aware scheme, and the M just means medium, a balanced size. That is why Q4KM is the single most recommended setting you will see. It is 4-bit savings, but smart about which numbers it protects, which is exactly why it loses only a % or 2. You will also meet 2 other names, mostly when running on graphics cards: GPTQ and AWQ. They are alternative quantization methods aimed at fast graphics card inference, and AWQ in particular is clever in the same spirit as that K scheme, using the model's own activity to spot which weights matter most and guarding those while aggressively shrinking the rest. The names differ, but the core idea is identical. Spend your precious bits where they count, save everywhere else. So how does quantization land depending on who you are? As an individual, this is the difference between local AI being possible or not. When you pick a model in Ollama, choosing the 4-bit version is what lets a capable model actually fit on your laptop and run at a usable speed, and now you know that you are giving up almost nothing to do it. As a startup, quantization is a direct lever on cost and speed even in the cloud. A quantized model is smaller, so it needs less expensive hardware and runs faster, which means serving the same feature for a fraction of the bill, as long as you have checked that the quality holds for your particular task. And as a large enterprise, quantization is what makes it economical to run powerful open models on your own infrastructure at scale. It lets you fit a strong 70 billion parameter model onto hardware you can actually afford and serve it to thousands of employees, turning self-hosted AI from a research luxury into a practical line on the budget. So let us bring it home. A model is just billions of numbers, normally written down at 16 bits of precision, and quantization rewrites each of them with fewer bits, usually 4. Cutting the size to a quarter while keeping nearly all the intelligence, because the model is robust to a little rounding the same way a JPEG survives, losing detail your eye never sees. 4-bit is the sweet spot. The smart formats like Q4KM protect the weights that matter most, and below 4 bits, the quality starts to break. This is the engineering that makes everything in the last episode possible. But we keep circling one number without nailing it down. How much memory does a given model really need, and what does your specific laptop or graphics card determine you can run? We have hand-waved at 8 GB and 16 and 32 long enough. In the next episode, we make it exact, and you will be able to look at any model and any machine and know the answer. VRAM, unified memory, and which models you can actually run. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.